Hello everyone and welcome back to the channel. Today I will show you a two-pointer technique with which you can literally solve 95% of two-pointer questions. Let's go ahead with it. So this is the two-pointer technique with which you can solve almost every single sum. This two-pointer technique is usually used when we want to find a suitable subarray or a suitable consecutive sequence out of your complete list of data. This is how this technique works. Suppose you will have many indexes from 0 to n minus 1, and in between you need to find a suitable subsequence or subarray. Okay, consecutive subsequence. So here your main logic is you need to find a suitable subarray for every ith index. That means if you have indexes from 0 to n minus 1. So suppose you have these indexes in your array and you need to find a suitable answer. So you will find the best answer from each I. That means in the first iteration, you will find the suitable array, keeping this index as your mandatory endpoint. After that, you will find the suitable array, keeping this index as your mandatory endpoint. After that, you will find the suitable answer, keeping this index as your mandatory endpoint. So basically, for each I index, you need to find a suitable answer for all the subarrays which are ending at this particular ith index. So that will give you the answers for each index. And then after that, all you need to do is either maximize it, minimize it, or add it based on your question. Now, doing this naively gives you a complexity of n square, but there are various techniques to make this process very fast. I'll give you an example by a question. In, in this question, you need to find a single consecutive sequence of operations such that throughout that sequence, the sum should not become non-negative at any point. That means you are starting with zero sum, you are iterating throughout your chosen sequence, and at any point you should not get a non-negative answer. So this is how you optimize such kind of questions. Suppose you are working on your ith index currently, which means you have found your suitable subarray for your I minus 1th position. Now you know that this answer is perfect for your I minus 1th index. That means all you need to do is use your I minus 1th answer and construct your ith answer. Now I'll give you an example. For an array like this, when I want to always keep a non-negative sum, first of all, keeping this as an endpoint, there is no suitable start point. So there is no answer for this index. For this index, this itself is the suitable start point. So your answer of 1 has your first index as your start point. Now, for answer of 2, you will use your answer of 1 to construct your answer of 2. This is how you save time complexity. Now, since your sum over here is 6, then you directly add this minus 6 and make it 0. Now, your sum is still not non-negative. So you can directly take this together and answer of I will become exactly equal to answer of I minus 1. But what if after including the ith element your sub-array becomes invalid? After that, what you need to do is you need to try to reduce your start boundary by 1 every single time. For example, suppose your answer of I minus 1 has your second index as your start point and you are finding answer of I. After including your ith element, suddenly the subarray is now invalid. So you increase your start pointer to third index and again check. Then to fourth index and again check. And so at one place or another you will definitely find your suitable subarray. If you don't find it, then the answer for that index is not valid and hence all of these indexes are gone. Now, how is this technique O of n and not n square? This is a very important concept. Now, as I said, your answer of I minus 1 had a start index of 2 and you are finding your answer of I. And let's say suppose you get a start index of 5. And for answer of I plus 1, you continue further. Now, for answer of I plus 1, I will not again start from my 0th index. I know that my previous answer stopped at the 5th index. So I will continue my search ahead of the 5th index. So this inner loop which you see executes a maximum of n times throughout the entire code. That means your final complexity turns out to be n plus n and not n into n. That makes a big difference. Okay, so this is the basic technique on how you can use the previous answer to generate your current answer. This is the first type of sums. Now, then the second type of sums are map type of sums, like this sums. You are given an array of n elements. You need to calculate the number of subarrays having a certain sum. Okay. Now, in this type of questions, we usually keep a map. And this map has data about your ith minus 1 indexes. Which means if you are finding the answer for your ith index, in these type of questions, you are considering all of your cases from 0th index to ith minus 1 index. And all of these answers are stored in a map. And so you need to directly refer the map and you will find the value for your ith index directly. Like example, I'll explain you the classic subarray sum question. Let's say you are finding a subarray sum with sum is equal to 6 and you have this kind of test case. Okay, you know by looking at this is a suitable subarray. Okay, so in this we are storing that what is the prefix sum up to your ith index in your map. Now, in different questions, only thing that will change is what we are storing in our map. In this question, since we need sum, we are storing sum in map. In some questions, we might need modulus or a combination of some two types or count. So we will store those things in our map. But since here we need sum, so we will store sum in our map. Now, minus 1 is present once. So I add it to my map. Minus 1 is equal to 1. Now, I go to my next index. Here my total sum is 1. I add it to my map. Map of 1 is 1. Now my sum here is 2. I add it to my map again. Here my sum is 4. I add it to my map again. Now here my sum is 6. If I know that my prefix sum up to this index is 6 and I want to calculate the subarrays having sum 3, that means I will have to remove all of the prefix which have sum 3. Okay, there have been a mistake. The sum up to here is 7. The sum up to here is 7. Okay. So if your sum up to here is 7 and you need to find subarrays with sum is equal to 3, that means you will need to try to trim out sum of 4s from your start index. That is when you will get sum of 3s up till this index. So you will take a look at your map and see if you have a sum 4 present. Since you have a sum 4 present, it is possible to trim off the starting point, and that gives an efficient answer for these type of questions. So thank you guys for watching. This was a basic technique by which you can solve almost every question of 2 pointers. So make sure to like and subscribe the channel and share it with other people.